Bismillahirrahmanirrahim. Good morning, students. I hope that all of you are doing fine and staying safe. Today, we are going to understand a primary component in the compiler construction process. How the programming language is defined and how the compiler is taught to understand the programming language. That is going to be our topic for the day. So we're going to study the BNF as a key component of the compiler construction. BNS stands for Backus-Naur form. Actually, these are the two individuals who came up with this notation and then refined it. It's actually a context-free grammar which can be used to define another language. It's a meta language. A meta language can be used to define another language. Why we need to use BNF? Because our usual human languages are context oriented. Whatever we say, whatever we speak, actually has its contextual meaning. The same word can have different meaning when it is being used in a different context. Computer cannot be taught the context oriented languages. Computer has to learn that one word can only mean one thing. That's what I mean by context-free language. Means you can use the word in any context and still it would mean the same thing. So the context is not going to affect the meaning of the word. Furthermore, our languages are not precise. What we say and what other people understand can often be different. Whatever we are trying to say and whatever other people are understanding, excuse me, whatever we are trying to say and whatever other people are understanding, that can be two different things. So BNF actually helps us to write a precise language, express the terms of the language in a precise manner, so it's accurate and unambiguous. Means there is no confusion in understanding the grammar of BNF. And again, as I mentioned, BNF is very essential in compiler construction because it actually tells the compiler how to make up sense of the word. I'm sure that you people have gone through the previous lectures of the compiler's front-end analysis, the lexical analysis, where we started to make the words out of the characters, and then the syntax analysis, and then the semantic analysis. All that depend on this Backus-Naur form. As I told you, it's a meta language, so it's worth explaining a little what a meta language is. You have gone through the dictionary at least once in your life. You would have to find a meaning of the word using the dictionary. Now in dictionary you see that we are using the English language to describe other English language words. The word synonyms you have done in your junior classes, where you are trying to explain a single word or a sentence using the simpler words and other sentences of the same language. So when we try to define a language using some other language or even that same language, that is called the meta language. So BNF is a meta language because it is used to define and describe other computer programming languages. Algol 60 was, I think, the first language that was used to define the Bacchus-Naur form. It is also must be kept in mind that the meta languages and the languages they define, they appear different. Just by looking at them, you can tell that the meta language and the language the meta language is trying to define, they both are two different things. Now we would try to learn about the components of BNF, means how the BNF will look like and what are the key components of that. First, these angle brackets indicate a non-terminal that needs to be further expanded. A non-terminal is something that can be further simplified, which has to be further defined. Symbols that are not enclosed in the angle brackets, they are terminals, means they represent themselves. They are atomic. They don't need to be further defined in terms of something else. They are defining themselves. For example, a parenthesis cannot be further defined into something else. It's a simple character. This symbol, the two colon signs followed by a sign of equality, means is defined as. The pipe symbol actually mentions the alternatives. The pipe symbol mentions or. For example, you can say a mathematical symbol can be positive or negative. So whenever we want to say or condition, we are going to apply the pipe symbol. So the angle brackets are non-terminals. The symbols that are going to be written without angle brackets are terminals. Then you have is defined as, and then you have your pipe symbol to show the alternative in the definition. When you try to write BNF, this is how it is going to look like. You have the thing that you are trying to define on the left side, and on the right side what you are trying to uh, write is something which is being used to define the thing on the left side. So here you can see that ID is defined as EXPR, and then you can see that EXPR is further explained here. So that means it is the EXPR is non-terminal because we are actually trying to further explain that. Let's try to go through an example to get this thing clear in our mind. So in the first example, what I'm trying to do is I'm trying to define a digit. So what I'm saying is that a digit is defined as 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Notice that there is no angle bracket around the digits 0 through 9. There is a pipe symbol which is mentioning the alternative, and the angle brackets are around the digit. Means digit is the non-terminal which is being defined using the help of terminals, which cannot be further explained, which cannot be further broken down or simplified. So I can say that my digit is going to be any of these digits from 0 to 9. Then I'm going to define something else, something that that you are familiar with, a natural number, and you know that a natural number is uh, all the positive integers. So I can define that a natural number can be a digit or a digit followed by the natural number. Now this type of definition is called recursive definition. You see that this natural number is being defined in terms of itself. I can say that a natural number is defined as a digit or a digit followed by another natural number. Means, in other words, means another digit. But this way of writing is called recursively defined. Something is defined in terms of itself. So what this definition is trying to say that a natural number can be, for example, 8, or it can be something like this, or even this. It's all the same. So any of these digits and any of their combination can appear here. And since we have recursively defined that, you can always try and choose this. Now I want to talk about this recursive definition's benefit, why we didn't write just digit followed by the digit. If we try to expand that, we can show that this digit, this natural number, is actually a digit, or we can say, taking this part of definition, this natural number is a digit followed by another natural number. Now that natural number can be, again, this natural number is equal to this part. So what I can write, this part of definition again, and I can say that natural number is equal to digit followed by another natural number. So what I can see that the digit can be 9 and this natural number will be still here. And then I can use this natural number and I can again use this part of definition, and I can say that a natural number can be this 8, 9, and a digit and another natural number. This is called recursive case. But this time I'm going to do that, I'm going to pick the first part of the definition of the natural number, that a natural number is defined as a digit. What I'm going to see now, that if I replace this natural number with a digit, it is going to be this. Sorry. So defining that natural number recursively can help me to define any number of digit values using this definition of natural numbers. I hope that it makes sense to you. Then I'm going to do this expansion again. This natural number is defined as digit and natural number. I'm again taking this part of the definition. This part of the definition again. Again trying to show you how this recursive case is beneficial to me. So what I can do is, digit can be replaced by any digit and this natural number is still there. Again I can use the same definition. The natural number is defined as digit followed by the natural number. The digit can be anything. For example, this time it is 7. And the natural number can be defined this time using just the digit, the base case. And this time I can say it's 875. So this is the benefit of recursively defining something. This is the benefit of defining something in terms of itself. If you don't recursively define that, then you will have to write different rules to define a 3-digit value or a 2-digit value or a 4-digit value. Recursively defining this actually eliminates this problem. Now continuing with our example, again with the same things, digit is defined as all the digits from 0 to 9. The natural number is defined as digit or digit followed by the natural number, and excuse me for this. Yeah, sorry, we're back on track. There is one more problem that can occur with this definition. Remember, we talked about the BNF is precise and unambiguous. Now, with this definition, with these two definitions, what can happen? The natural number can be zero, because we said that natural number can be a digit and the natural number. So, what can happen is the digit can also be zero, and if we expand that, there can be a case where the digit can be expanded to 07. So, but we don't write 0 on the left hand side. What we do is we always start with our values with a non-zero digit. So this is another problem. What we have to do is we have to again define our BNF in a way that the value doesn't start with the 0. So this time I'm going to define, first of all, a non-terminal named non-zero. The non-zero is going to be these all digits. And then I defined something that is a digit, and the digit can be defined as a 0 or a non-zero. So now I have a more precise definition of the digit, that a digit can be a 0 or it can be a non-zero. And non-zero is defining all the digits from 1 to 9. Now I'm saying that a number, I'm defining another thing called a number, that a number can be a digit or it can be a digit number. Again, number is being defined recursively. Now we have everything that we need to define the natural number. What we do is we say the natural number can either be digit or it can be a non-zero and the number. Now in this case of definition, a natural number can always be expanded either to a digit. The digit is 0 or non-zero, but it can only be done when it's a single digit. Whenever there are more than one digits, the first digit is going to be the non-zero. And the second one can be anything from the numbers non-terminal. And numbers are digits and numbers. So in the second place, a 0 can occur. Now using this definition, you will never see a case where a 0 is in the leftmost position of the value. So this is how we can define anything with precision, with no ambiguity, and a computer program, our compiler is now able to understand exactly what we are trying to say. It is now able to exactly determine what a natural number can be. This is how your compiler lexical analysis makes sense of the word. Another example, this one is straight out of the book, the course book. I'm sure you're already having that. I keep referring to that in my lectures. You should always go through the topics on your own, as this is not a face-to-face session. You should always go through the topics from the recommended book as well. So what I'm trying to say that is that an identifier is defined as a letter or an identified and letter or an identifier or a digit. This pipe symbol is again Since there was no space in the line above, so it's in the next line. Don't think it is something new, it is actually the part of the definition of the identifier. Now we have that digit and the identifier and the letter. So we have to define the letter and the digit as well. Because a non-terminal has to be defined in terms of terminals. This non-terminal, which is an identifier, is being defined in terms of other non-terminal, like this letter and this identifier and the letter and the digit. They are all non-terminals. So we have to further define them using the terminals. So a digit is this, and then we say a letter is defined as uppercase letter or lowercase letter. Again, they both are non-terminals. What we do is we take the uppercase non-terminal and we define as what an uppercase can be. An uppercase letter can be anything with a capital A to capital Z. And then a lowercase letter is also defined from small a to small z. So what we have said, that identifier non-terminal can be a letter, and then we went ahead and defined the letter. And the letter was defined in terms of the uppercase and lowercase, and then we defined them as well in terms of terminals. So now when a computer would see, when the compiler would see an identifier, it can easily make sense whether it's a valid identifier or whether it's a non-valid identifier. For example, if we write an identifier like this, the compiler is going to recognize that as a non-valid identifier according to these definitions. And if we write that like this, the compiler is going to recognize that as a valid identifier because the definitions are actually clear enough for the compiler to understand what an identifier is. The last thing that we need to look at are syntax diagram. Rather than writing the BNF, we can always make a diagram of the syntax of BNF and show that. The syntax diagram actually can show the same thing, but rather than writing that in the previous notation, we can make the diagram of that. In this syntax diagram, we are saying that a digit can be anything of from 0 to 9. Notice that all the arrows are actually originating from one single line. Means a digit can be this or this or this. This is how we define the OR thing. Then we have a letter. Due to the less amount of space the diagram is squeezed into, a letter can be defined as all the letters from capital A to Z or small a to Z. And since they are all originating from the same line, so that means a letter can be A or B. An identifier can be defined as a letter. And then what we are saying is a letter, follow the arrow, is a letter can be either a letter and it can also be a letter and digit. And then a letter can be a letter itself. So this is the recursive definition. This arrow which is actually going back to the letter is actually the recursive way of defining the letter. Mostly we use the previous notation that I have showed you. Syntax diagrams are rarely used because syntax diagram cannot actually show the complex definitions. So that would be all for the day. Now we are going to move to the question answer sessions. Thank you all.